Hi, everyone. Paul Bemis here. I'm going to be doing a webinar today on predicting data center thermal performance during a major grid outage. A couple of things about today's broadcast. For one, there's major construction going on outside of my office, and you might be able to hear it. Number two, we're experiencing some power interruptions here, which is ironic considering we're talking about major power outage in the presentation. So if I go dark for a moment and my voice drops out, I've noticed it's just transient and it's just flickering, but it causes the router to cycle. And I have one of my colleagues is on the line, and I've made him organizer, so the presentation won't stop. It won't go dark on you, but I'll drop out and then I'll rejoin as soon as I can get the system back up. Okay. A couple other just housekeeping things. This is a webinar, so this is presentation mode. If you'd like to ask questions, there's a chat question block. Please ask them as we go. That way I can address them and answer your questions as we go. I think that's better for you and better for me than waiting till the end. So queue them up using text. Just use the little question box in the GoToMeeting interface over there on your right. Okay, I think that's it. My name is Paul Bemis. Most of you know me by now. We're going to be talking about transient analysis using computational fluid dynamics. So the basic issue we're all facing here is higher densities. I'm seeing a lot of this, much higher densities in data centers, and that trend towards the trend of trying to lower PUE is making it more challenging for the transient case, the power outage case. As you drive down PUE, what's typical is people use hot aisle, cold aisle in their designs. They increase their supply air temps, trying to drive that number down. I know that some providers are trying to, their goal is to get that number down as close as they can to 1, 1.1, things like that. To do that, you're going to be driving inlet temps up and supply air to only what is required by the racks. They do help in the steady state operation and do lower overall PUE, but they reduce the margin of error in case of a power interruption, like the one I may face today. So I'm going to take a look at a few cases and just show you what happens. This first one is a classical case. I think this is an old IBM data center that has been around for a long, long time. And the point here is that it's non-contained. So you see this is a downflow design, very classical. We call this convective return. So you have the cooling units over here in blue, and then you have the tiles here, the floor tiles. This is a raised floor design. So the air goes down through these cooling units into the floor, up through these tiles over here. And so it's a very conventional design, if you know what I mean. So what happens is in the case of a transient case, so this one happened to be set up so that it's running at a return air temp of 75, a supply air temp of 60. So you notice right away that's not very high. That's only a 15-degree delta. You want to see that number higher than that. A good efficiency in data centers is when you have this number at least a 20-degree delta from the supply air temp. That means you're getting good heat transfer to the returns. You'd really like to see it closer to 30 on new designs. The RTI, for those of you who have been through the DCEP training, RTI is 99.4, which means we're only supplying a little less than 1% more air to the room than is needed by the racks. That's what you want to drive this to 100%. This is the ratio of demand air divided by supply air. So it's always should be less than 100. And you want it to run close to 100. I mean, perfect would be 100. You're only supplying what is consumed by the racks. That's hard to do, of course, but that is the goal there. And then this one is, are there any hot spots? You want this one to be above 95. If in the DCEP training you try to get these two numbers as high as you can. RCI low is 15. That means we're running too cold. That doesn't hurt the IT equipment, but it's inefficient. You can see our supplied air temp is 60F, so that's simply too cold. So this data center is operating in a situation where they're running it cold. They really have to because they're mixing their air pretty well because they don't have any containment. However, what the good news about this room is the room itself is full of relatively cool air. So if those air handlers go down, there's volume. There's volume in the air to help you make it through that transition period. So the information that we need to know in order to do transient, and we've been doing a lot of this lately, is what do the fans do and what does the cooling system do as a function of time, right at the point of time where the equipment turns off, okay? So what goes on? And there's two components to that. One is we need to know what the fans are doing. And the other one is how's the cooling system? There's usually a reaction time on the cooling system. It takes some time to react, to boot back up and to start throwing cold air again. The fans, however, are a little easier because they're just fans. And in many cases, you can get those up quicker than you can the cooling capacity. So in this particular case, this example, what we're seeing here is 10 seconds. So this is diesel generator start generally. And by the way, these things generally aren't backed up with battery. It's too expensive. So there's no UPS for the cooling system typically, although some data centers have that. So in 10 seconds, the generator's up and running. I think that's pretty generous, by the way. But generator's up in steady state, 10 seconds. You start to ramp the fans. Now, this is really important, is how quick you can ramp these fans. And then you go through a ramp, and up at 25 seconds, you're at full tilt. Well, pretty much, 30 seconds, you're at full, okay? Now, the cooling capacity doesn't come in for 120 seconds. So that's kind of tough, right? So let's take a look at this plot. Now, this is a plot we've been generating lately, and I come to really like it. It's a little tough to look at first because it's busy, but it's got a lot of information in it. So what we're doing here is plotting the maximum rack inlet temperature as a function of time for every rack inlet in that room. And what you see here is at T equals 0, things get hot quick for some racks. Now, every color is a separate rack. You can see some racks are actually fine. They're okay for a period of time. And those could be lower density racks often, or in a position in the room where there's cool air. And that is often, there's a gradient in the room anyway of temperature. And so they're just hanging around a place that's cool. These, on the other hand, could be high density racks and are in a hot section, like close to the cracks in this case, because that particular data center has issues with the racks being too close to the crack units and the perforated tiles not delivering the air they should. So what happens is you have some racks that almost immediately start shooting up in temperature. They get to a certain point and then you see those fans come on. So here are the fans coming on right here. And what happens here is that, of course, the plenum is full of cold air. So you get this immediately shot of cold air entering the room. So bang, a lot of it goes right back down because it's getting nice cold air. Even the ones that are hottest are beginning to come back down. So that's pretty good. And then you can use that capacity, that cooling capacity that's inherent, that's latent in the room to ride this wave. So you basically got the fans running, you've got the IT servers running, and you're mixing everything in that room, and you get 60 to 100 seconds of time in a non-raised floor data center that's conventional. This is how things have been in the past. This is why many people have confidence that they're going to be able to make it through this transition because this is what history has looked like in the past. When you talk to people about what do you do in a transient case, they all go, yeah, well, we've been through one, it worked. Well, it may have worked before, but it's going to get tougher. So here we have just some conclusions to this. The IT servers start recirculating on themselves, usually over the top. They usually drag air up over the top and around the sides. If you can bring those fans back online, the cold air comes up out of the floor, which is sitting there. It's heavy anyway. So it's sitting there on the floor, you pull it up out and get it in the room, and you can ride that for 120 seconds, okay? However, here's another design, and this is a very classical design. I've showed you this before. This is a common design I see today with high density data centers, is they're using basically a fan wall technique. You can call it many different things, but fan wall is a clear representation, and you have the air handlers over here in blue, and then you generally have some kind of screen wall in front of it to try to distribute the pressure a little more evenly if one of those blowers is off. And then you have the room, and this is hot aisle containment, ceiling grills, and racks. And the red represents a leaking baffle or leaking membrane, because there's leakage in containment. Containment is not perfect, as most of you know. So what you do is you simply try to keep the pressure gradient in this room positive from the outside on the room side, rack inlet side, to the hot side, which is inside this contained area, okay? Now, this one happens to be about 1.8 megawatts, 7,000 square foot, pretty high density. PUE typically operates in this range, 1.2 to 1.4, depending how well they've done their homework. They typically use fan coils over here. These are not DX units. These are usually fan coils supplied with some kind of medium, either gas or liquid from the outside. And the supplier temps tend to be a little higher here. We're trying to get them up to get that PUE down. Return air temps, you see here, we've got a better delta now. We've got at least 20-degree delta, 25-degree delta. That's getting a little bit better. RTI 96, which means we're only supplying 4% more air than is needed by the racks. RCI high 92. There's a couple of hot spots there, but I think our friend Magnus would say that's probably good. You'd like to see this one 95 and this one 95 or above, and RCI low 100 because there's no cold spots. But what happens here is that if you lose power, and this came from one of our partners that's in the cooling business, what happens here in this particular case at T equals 0 is the fans go to 0, and the cooling system doesn't come back on for 70 seconds, and the fans begin to ramp after a few seconds, but the ramp is a little slow, and then it comes up, and then it goes across. So you have here about 20 seconds, 25 seconds of ramp on the fans, and then you have 65 seconds before the cooling comes in, and the cooling comes in stages. In this case, stage 1, stage 2, stage 3. These are various compressors they're bringing on sequentially. This time lag right here is associated with the cooling system itself, the software and the hardware, and they're trying to protect it, so they can't turn it on like a switch. They have to ramp it. So that's what's happening there. Very typical. This is a new system, so this is relatively current information coming from one of the major cooling suppliers. It takes time to reset those systems. So what happens is you have an imbalance right away of pressure. The pressure in the room suddenly drops below what the pressure is in that contained area. In other words, the pressure gradient inverts because there's nowhere for that air to go. The cooling units are down, so now the IT servers are trying to push air into a contained area that doesn't have anywhere for it to go. It's a pressurized vessel in a sense. It does leak pretty good. In other words, the fans on the air handlers are not completely sealed. They do leak, they do let air pass by, but the IT servers are not designed to push that much air, and they accumulate it in the contained area, and it begins to bleed back through the containment locally. It doesn't really make it all the way through that loop very well. Air's lazy. It'll leak out where it can. So what you see in this plot is very quickly we have a problem. Now these numbers are small, so I'll read them to you. We go from 70 degrees supply air temp to 110, this is 120, this is 130, 130 degrees of rack inlet temp. Now this is max inlet temp, so this could be anywhere on the rack inlet, but that's what you're seeing is within 30 seconds, you're already at 130 degree rack inlet temp. This thing just goes really fast, and it's because of that inversion. of pressure. It causes it to leak back through the grills, back through the blanking panels, the rack rails, the edges between the rack and the contained area all leak, and it pushes it back out into the room. It gets sucked into the intakes. Furthermore, if the pressure gets high enough, the IT servers will start to walk a fan curve where they can just no longer push any air at all, and then you have a very, very rapid increase of temperature on the circuitry itself. And then fans kick in, you get a flush of cold air again, coming from the latent temperature that's in the cooling system from the air handler to the rack inlet. And then that bottoms out pretty quickly. You notice that's bottoming out in really just 15 seconds. Because for one thing, you're running at high supply air temps, so there's not a lot of room for margin there. You're already running at 70 degree supply air temp. So it comes down, cool air is depleted, it starts going back up again. And here, cooling capacity begins to be added, and at 80 seconds, we get to a peak, and this tail is quite long to get that system back down. This is a 90-second plot. And this is what it looks like. I'm going to pop this. I want to show this. I've showed this to you before. It's a little hard to see in this image, so I'm going to pop a 3D image here. One of the great things about CoolSim is you can do this. And I'm going to show this to you in 3D here. And this is, you can see I've done a cut plane or a contour plane at 6 feet. And here we're looking at temperature. And what I want to show you is that if we move this thing to the Y plane and I turn off perspective, you can see what's happening is that pressure gradient changes. So the pressure situation is such that we have less pressure out here than we have in here. It should be the other way around. This should always be, this is outside the rack. This is the room. These are the racks. Should always have a positive pressure gradient from the room to the containment. And if you don't, this starts to happen. It just bleeds back through. These are the rack rails of the containment. Typically, that's where it happens. So these are the servers themselves. This is the gap between the server and the next server. So the sequencing here. The problem I was talking about earlier, just before we lost power, is that we have a situation where, again, let me just flip this around. By the way, I've got a little construction going on outside. That's what's causing this problem. But you see the leaking right here. It comes blasting through. Now, in this model, what I've done is I've represented the racks as servers themselves. So this is rack rail leakage primarily here. This is inside the rack. There's not much you can do about it. It's going to come pushing through. It also, by the way, is the same issue when you have between racks. So this is containment, and these seals along this edge right here are not perfect. This is why you need a positive pressure gradient from the room itself into the contained area. So I thought I'd just show you that. I've showed you that before. It's a good representation of what's going on in the room and works a lot better than just an image like this, okay? So when you operate at low PUEs with containment on hot and cold aisle, the transition from grid power is more sensitive, and this is going to continue to be more of an issue as we go to higher density. You have less time. And CFD modeling is really the only way that you can predict the outcome and have confidence in it. You really can't test it. Testing this is crazy because in order to test it, you'd have to load the data center with equipment. Load banks don't represent servers very well. That's often what's done for commissioning is load banks. And you never know what you're going to have in the room. So trying to do it physically is near impossible. Very expensive to do, tough to do, and doesn't have very good outcomes. CFD modeling is a way for you to predict it with fairly good accuracy. We've been doing transient analysis in CFD for, oh God, I'm getting old, 30, 40 years now. We know how to do it, and it's been validated over and over and over. So it's quite predictive. It's quite good. All right, so let's take another one. This is an interesting one as well because not all data centers are the same. This is one that we worked on a while ago for Data Center World one year, and Here we have a typical situation where you have fan coils in the room and air handlers in the room. You have a chiller of some kind, and then you have a cooling tower. This equipment over here is not that important, but this one right here is. Let me use my pointer. This loop is important because if this loop has chilled water in it, and this pump can be put on backup so that pump remains running, and these fans can be put on backup so they can remain running, you buy an awful lot of time. Basically, you're using capacity. You're using cooling capacity. Now, sometimes data centers will use a cooling pond, or sometimes I've seen them generate ice. They actually produce ice and use it. In other words, they need a reservoir of cool something to allow you to ride through that transient period. So here's the data center we analyzed. This one is non-raised floor, ducted supply in this case. They're blowing it down from on top. And we've got two chillers in this case working. One of them's in standby. We've got a flow rate, we've got a length of pipe and a diameter of pipe and a mass flow rate. And we know how long it takes to complete a loop. So we're going to study two cases here. In the first case, well, here's just the data. We've got 532 gallons of water floating around the campus. That's really good, particularly if you've got backup on the pumps, because that means you can use this to buy time until you get your chiller back online. Loop time is about 66 seconds. In other words, the time for water to come out of our data center that we're interested in and all the way around back to our data center again, about 66 seconds. So first we'll do a full system failure, and then we're going to do one with the pumps and the fans backed up. So case one is the inlet and outlet of the air handlers are assigned a wall boundary condition. We just shut them off. Now, not quite true. They do leak a little bit of air, but not much. The fans are on the IT system is really going to recirculate on itself. Once those fans go down in this design, because it is not contained, there's no pressure delta across the air handlers at all. So they're just going to not produce any cool air into the room. So we assigned boundary conditions of walls to them. We didn't let any air go through them. We have a simulation time step of 0.01 seconds, which means we need 100 of these to give us 1 second. Another thing about transient is, from a CFD point of view, it's computationally intensive. You have to do a full steady state solve at each time step. So for 1 second, I have to do 100 solves, and each solve can take a couple of hours. So the amount of time required to do these analyses is long and computationally intensive. But it can be done, and the results are fairly representative of real-world situations. So this is what happens in this case. This is rack inlets as a function of time, and you can see that 3 seconds they're getting hot, 5 seconds they're hotter, 9, 12, 14 seconds, we're already well above where we want to be on rack inlets. And you can see it's happening right at the top of the racks. It's going right over the top and bleeding into the inlet. So we've got air coming right out of the exhaust and right into the inlet, non-contained case. So within 9 seconds, we've got issues already. Rack inlets, particularly in the center of that room, and things get out of hand quickly. Now, in the next scenario, scenario 2, we have the chiller going down, but the pumps and fans are operational. And so we have a reservoir of water traveling through this loop right here. And that we've already calculated. It's a little over 500 gallons. It gives us 66 seconds before it comes out. The chilled water downstream is consumed in 33 seconds. So every 33 seconds, because it's only half, right? In other words, you really only have a shot of water from this. Well, I'm going the wrong way. Yeah, from this device over to these, that's half the loop. So that's 33 seconds, and then it comes out hot and heads back. Therefore, you get this step, and this is kind of an interesting situation. You have temperatures rise because the fans are off, and then you get a slug of water that comes through. And that provides some level of cooling. These are air handler outlet temperatures. And then after 33 seconds, it steps again, because that hot water has made it from the last trip through, has made it back to the air handlers again, and you get this step, and then you get this rise again. So this buys you time, is really the point. So you get a stepwise relationship between the air supply temperature due to the slug of water, cool water coming back through the cooling units themselves. And so you have more time. So here now we have 33 seconds, 41, over here 49, 50 seconds, 57, 65, 73. 73 seconds, a full minute into it, a little over a minute into it, we're just beginning to see elevated temperatures in one section of the room. So very few places reach 90 degrees, which is, we're talking here about the acceptable inlet temperatures recommended by ASHRAE TC99. So not too bad. Even we can go all the way to 121 seconds and things are still not too bad. We get a couple of minutes of time before we really have to worry about things. And even then, it's only certain sections. So if we look here, we're hot just right on the ends, which is typical, and at the peaks. And oftentimes you're not necessarily loaded right there anyway. So this is a very, very encouraging kind of representation. So to accurately predict it, you need to be able to do a transient. The transient should be built and should be analyzed based on your case. You do this by building first a steady state model of the data center as it is. The way we do it here is we have you, the user, or we can do it for you, build a steady state model in CoolSim. CoolSim is a steady state device at this point. We have not introduced transient to CoolSim. However, Fluent is behind CoolSim. CoolSim is really just a front end on Fluent. Fluent is the Ansys CFD tool that's been around for 30 years or so and has a tremendous amount of mileage on it in terms of calibration and validation and transient work. So we take the steady state model out of CoolSim and we read it into Fluent and we perform the steady state analysis on your behalf. We do that because it's quicker and it takes a little bit of expertise to do a transient. You have to have good convergence on the first step. That's a human in the loop situation where you're working with that first time step to make sure it converges to a criteria that is acceptable. And then you go ahead and take the next step and further on down the road you go. So you build a steady state, calibrate it, and then we go ahead and do the work. We, however, need from either the customer or the cooling supplier a representation of fan performance and cooling capacity that has to be provided as well. And each of these situations is unique, and the cooling systems are all a little different. For example, some of the evaporative cooling systems are better at this kind of response than the traditional compressor-based systems because the reset time is quicker. I mean, if it's evaporative, it's going to evaporate. It's going to continue to work even though you may have gone through a power spike. Unlike the compressor-based systems, which often have to go through a full reset system and make sure that the flows are correct so that you don't freeze a coil to damage the equipment. So the startup on a compressor-based system, whether it's a DX or a chiller or some other type of system, generally takes a little bit longer because they're bringing it up in a sequential fashion to ensure they don't damage the equipment. But in any case, it's likely that the customer, you or us, will have to get involved with the cooling supplier to understand the information related to fan performance as a function of time and cooling capacity as a function of time. And using CFD modeling to do this is time consuming and data intensive. Yes, that's true, but it's the best way to do it. Time steps need to be short, so this takes a long time to run these things. Generally, it'll take about a week of processing to do a computational study like this, and that's running on a cluster with lots of processors and lots of cores and lots of memory. But that's something we do it all the time, and can help you with it if you're interested in doing this. We've done it for a long time. Most of my team has extensive experience. in doing this kind of work, and we can help you if you're interested. So that's it. I'm sorry about the power outage here today, the transient power situation I'm facing. I have extension cords all over the place now trying to plug into different outlets because my UPS seemed to quit right in the middle of this whole thing. But I'd be certainly willing to take any questions that people may have. If there are questions, we've got 21 attendees, and if you have any questions, we'd be willing to take them right now. Otherwise, we will call it a day and rerun it again in the future if you would like to see it. I don't see any questions. And I see power surging here again. So I'm going to sign off for this webinar. I want to thank you all for attending. If you have any follow-on questions about this or you want to talk about it more, please feel free to reach out to me and we'll pick it up specifically, okay?